Next, I'd like to invite Paul-Antoine Arras from BayLibre for his talk.
Thank you for the introduction. So I'm going to tell you about the analysis that I've made on the code generated by GCC for RISC-V and compare it to ARM. So yeah, a few words of intro, and then I dive into the results of the analysis, focuses on the weaknesses and deficiencies of the compiler on one side, but also on the ISA, and also a few words also about the library routines. So first, a few words of context. So this work is a collaboration between BayLibre, but also Rivos, and it is funded by the RISC project. So I refer you to Trevor's talk half an hour ago for the details about this collaboration. So previous work has shown that in most benchmarks, the code generated by GCC for RISC-V traced ARM, in particular AArch64 in terms of performance. And so that begs the question, how can we improve the code generated by the compiler, especially by GCC? So it is thought that large gains can be made. And to do so, we have picked a vendor-neutral metric, which is the dynamic instruction count. So granted, this metric has its flaws. We know it, and I show a good example of that later. But for this specific study, when we want to analyze the assembly of the hotspots, which are the basic blocks of code that take the most time of the run of the benchmark, for this kind of study, we found that it served its purpose. So few words about the experimental setup that we used. So the target architecture are ARM with DSV2 vector extension and RISC-V with the V extension. We're targeting an architecture that is close to the Banana Pi F3 board, so with 256-bit vectors. And we use SPEC CPU with the reference dataset. We build with the fixed version of GCC, both for AArch64 and for RISC-V, and use user mode QEMU to run the benchmark with the plugin that was provided by Rivos that allows us to determine what are the hotspots in the code and to get the assembly directly. So I've got two bar charts showing the same data but with two slightly different views. This one is showing the absolute numbers in terms of a dynamic instruction count. So in blue you've got the DIC for ARM and red for RISC-V. So here smaller bars are better. So you can tell that for most benchmarks ARM achieves a better, so lower dynamic instruction count. On this second view, you've got this time the relative difference between RISC-V and ARM. So ARM being taken as the reference here, and you can see that some benchmark like a GCC or Cactus or Arras exhibit like a quite significant difference. So we're going to focus on those benchmarks in our analysis. I'm going to give you 4 examples of issues that I found during this analysis. First, something that is directly related to the ISA. So for instance, on the Arras benchmark, we have shown that there is a 54% difference compared to ARM, even 56% if we just focus on the first top block, which comprises mostly this tight loop. So well, this code is really simple, but it has 3 times the same operation, so dereference and increment. And for each of those operations, we've got 3 operands: the base address, the index, and the element size, which in this case is 4 bytes. And we compute the effective address by adding to the base address the index shifted left by 2 in this case. So if we look at the assembly that's generated for this kind of operation, for ARM it's pretty simple, just one instruction, one load, that's adding the base address in X3 to the index in X0, shifted left by 2, and the result is loaded into the vector register Z30. Now, if we look at the equivalent code for RISC-V, we see that we need 2 instructions. So first we need an add immediate instructions to compute the offset into the array. and then a second instruction that's going to do the load itself. So here, the offset, the address is computed into T1, and then the result is loaded into a vector register V4. So just one example of an addressing mode that exists in ARM but doesn't have an equivalent in RISC-V. I've got many more examples of that in the extended abstract if you want to take a look later. So now, another category of issue that I found, this one is directly related to the compiler, and this has to do with vector instructions that have two flavors. So it's the case, for instance, of VFM add, which is a vector floating point multiply add. This one has two flavors, one with only vector operands, and a second one called the VF1, which also has one scalar instruction. And if we look at the ROM's benchmark, we can see that we have a number of instances of this snippet, so the sequence of a vector floating point move instruction followed by a vector floating point multiply add. And you can see here in blue, the V6 register is being reused immediately. So here, obviously, we would like to combine those two instructions into a VFM add VF this time, from which we would directly use the content of the register FA4 rather than having to resort to a move. So I submitted a patch to the GCC mailing list for that. This patch comprises a new instruction pattern for GCC to be able to generate the code, and also a new cost model. With this patch, I've shown that I got a dynamic instruction count reduction, some ROMs, which is the benchmark on which I did the analysis, but also on B waves, actually I'm getting an even better reduction, minus 4.7%. But now the question is, does that translate into actual performance gain on the real hardware, on real design? So we tried on the Banana Pi F3, and the average over 3 runs is, so on B waves, we get only minus 0.33% of reduction. So of course, not as good as what we'd have hoped, but still some reduction. So now the third example of an issue, implying the compiler, but also related to the library function. So this time we look at memset, which is heavily used by the GCC benchmark. And here we can see that RISC-V is calling the glibc implementation of memset, is spending 21% of the run, actually, to be precise, in glibc memset, while ARM only spends less than 1%. So that's quite a significant difference. So we looked into that to understand why we see that difference. And actually, we need to understand what's the strategy that GCC uses to produce code for built-in functions, because memset is one of those functions that are well known to the compiler. So the first possibility, the best usually, is for GCC to expand directly the built-in without having to call an external library. ARM does that most of the time, and the result is pretty simple, like 5 instructions. But then, if it's not possible to expand, then a call to glibc is made, so either to a hand-optimized version of the function, or in last resort, to the generic scalar version. And that's what RISC-V is doing, and that results in 46 instructions, which makes quite a big difference compared to ARM. So there are a few things that prevent the compiler from expanding the call. One of the things is that by default, the maximum vector length multiplier for RISC-V is set to 1. But there are also extensions to the RISC-V ISA that could help, but that are not necessarily available. And also depending whether the f-inline string ops option has been passed to GCC. Now, one last example, implying also the compiler, some library, but this one with an ABI component. So I look at the ROM's benchmark, and I saw that the __exp function was used. So in ARM, only 1.55% of the run, and RISC-V 6.48% of the run. But actually, if you look into the details, you see that this __exp function is only the generic scalar implementation, which is in libm. But actually, it's possible to have a target-specific vectorized version in libvecm, and that's what ARM does. And actually, 80% of calls to the exponentiation function end up using this target-specific vectorized and so much more efficient version. On the other hand, RISC-V doesn't have such an optimized version, so it results in 32% more instructions. So a few things that RISC-V can do to catch up, and that is already doing actually. First, working on the ABI to address name mangling. On the GCC side, enabling the SIMD clone pass, and on glibc, well, writing the vector implementation. So all those 3 points are already being addressed by the community. There are patches being reviewed at the moment. So just to conclude, a few words about what I'm doing now, because this analysis is still ongoing. So I got a review for my vector scale-up patch. I'm working on a RISC-pin. Then there are other analysis to be done. So the initial analysis was done on the earlier version of GCC, I think fixed in August, but since then a lot more work has been put into RISC-V. So I have to refresh the analysis based on the latest version of GCC, so GCC 15.1 that was released I think last month. And so yes, I'm redoing currently this analysis with fresh data. That's all for me for now. I've got much more details and more examples of what I found in this study in the extended abstract, which I think will be available on the conference website, which concludes this presentation. So thank you for your attention.
Thanks a lot, Paul-Antoine. Is there any question from the audience? Oh, over there.
Hello. Yeah, great stuff. I just wanted to ask if when you report these numbers, if you can get in the habit of having people report dynamic byte count as well as dynamic instruction count. Because part of the RISC-V design is the compressed instructions. So to get at the differences, it'd be good to have dynamic bytes fetched as well as dynamic instructions.
Yeah, so in this analysis, yeah, we just counted the number of instructions. We didn't count dynamic bytes or anything else, well, which makes the analysis quite partial. But yes, we run when we find the first top blocks of each run. Then for each snippet or each basic block that we're really interested in, then we run more analysis on the BPI, on the banana pipe board, and then we get the actual timing. But yeah, we need to measure more metrics like the number of cycles to get like proper performance results. Yes, because definitely the instruction count is not enough.
And just yeah, the bytes would get at some of the design choices we made separately from ARM. So, and that doesn't need any microarchitecture. It's just an architectural level measure, like how many dynamic instruction bytes did you fetch? So,
yeah, that's true. Well, that metric wasn't part, but yeah, for the next round of analysis, yeah, that's definitely something we should have in mind. Yeah. Thanks for the suggestion.
All right, let's thank our speaker again.